Good morning. I'm Caroline Troop-Gill. Welcome to this news briefing from the 252nd National Meeting and Exposition of the American Chemical Society in Philadelphia. We're joined today by Dr. Paul Slesinger from the Mount Sinai Medical School and Dr. Ann Andrews from the University of California at Los Angeles. They are both presenters in the Kavli Symposium on Chemical Neurotransmission later this afternoon, and will be talking to us about their latest work on detecting signals in the brain. Dr. Andrews?
Yes, thank you very much. We're very excited about the symposium this afternoon. I had the opportunity at the invitation of Diane Schmidt-Grob, who is the ACS immediate past president, to put together a symposium that would address President Obama's BRAIN initiative and to try to choose speakers who would best exemplify how chemists might become involved in the BRAIN initiative. So our goals are to highlight some of what we think is the top research by chemists involved in this initiative, and to hopefully encourage others through this forum to think about how they might direct some of their own research toward this initiative. So we're very excited about that. And Paul is one of our featured speakers, as I am as well. And I think it would be wonderful to hear a little bit about Paul's specific work.
Sure, thank you. So taking a lead from that, one thing that we're very interested in is trying to study the chemistry of the brain. And we're interested in looking at how neurotransmitters and neuromodulators are released in the brain during certain behaviors. And the type of technology that we're developing is one that would allow us to do this by creating this, what we call a biosensor that we could implant into the brain, and then using optical methods measure the light that is emitted from these. The technology is shown here on the right, and in this slide. And the way we are creating these is to take a receptor that's also present in our brains, but we take this receptor and we place it specifically in a unique type of cell that is coupled to a light sensor. And then with this light sensor and the receptor, which we refer to as a biosensor or a sniffer, we can implant this into the brains of mice. And then through a very tiny window, we can peer in through the window and then study the activity, the light that's being emitted from these biosensors. And what we hope to find is that under certain behaviors, the biosensors will become active, and at that time we can see when a particular neurotransmitter is released. For example, we show this one type of graph here where we can see that the green and black lines, when they go up to the top of this graph, that occurs precisely at a time when this animal, it's a mouse, is licking to receive a reward. And that reward occurred after a tone. And what's unique about this technique is that we can measure two of these chemicals simultaneously. So in this example, we're measuring two, dopamine and norepinephrine, two chemicals in our brain. Then over time, we can measure the timing of this release as the animal learns to develop a specific behavior. And in this particular experiment, what we're doing is pairing a tone with the reward. And what we found is that the timing of the release of that dopamine signal moves in time with days of training to go from the reward to the time of the tone. We hope to be able to develop this technique to study more neurotransmitters, chemicals in the brain, and to be able to study animals that are awake and behaving, so they're moving around and exploring their environment under these conditions.
Great. Would you like to tell us about your research?
Absolutely. Thank you, Paul. That was a wonderful description of your work. We're also working in this field of chemical neurotransmission. So neurons don't actually touch each other, and when they communicate, they release these chemicals called neurotransmitters. And so one of the ways that chemists have been trying to understand how information is encoded in neural signaling is to develop methods like the one that Paul just described to study chemical neurotransmission in real time in the complex brains of animals that are actually performing tasks similar to behaviors that humans perform. In our own research, in my research, in collaboration with Paul Weiss and Yang at the University of California, Los Angeles, and also in collaboration with Milan Stoyanovich at Columbia University, we're making sensors that are similar to what Paul described, but we're using a slightly different technology. We're also developing receptors, which are important for allowing us to identify each particular neurotransmitter. Our receptors are slightly different than Paul's. They involve nucleic acids instead of proteins, and our receptors can be highly engineered. In addition, instead of coupling the receptor's action to light, which is what Paul is doing, in our work, we couple the receptor's action to a field effect transistor. So we're actually trying to take technologies that everyone is familiar with, that we use in our computers every day, and we're trying to take that technology and develop it so that we can actually use it for brain sensors. And like Paul's work, we'll be doing this work in animals, experimental animal models. But we also see potential for these kinds of sensors to possibly be used in human beings. For instance, in combination with something called deep brain stimulation, which is a treatment, is a current treatment for refractory Parkinson's disease. It's also starting to be used for neuropsychiatric disorders. And so we can imagine the sensors that we're developing being coupled with deep brain stimulation to give feedback about how the stimulation is working and how it may need to be tuned for individual patients.
Good. Thank you. I'll open it up for questions from the floor. We've got I ask that you use the microphone and state your name and affiliation before making your question.
So it's Kath O'Driscoll from Chemistry and Industry magazine. You mentioned about the potential applications in people, and I'm just wondering if you could tell us a little bit more about that and what hurdles need to be overcome before you can actually get to the stage of using them in people.
Yes. So I think probably the major applications for these types of sensing devices is going to be in experimental animals. But as I mentioned, I think there are going to be possibilities for implanting these in people. Of course, we'll have the hurdles to overcome that we would with any medical device, getting them approved by the FDA. But I think long before that, we have the hurdles of the research and development. We need to try to understand, through our use of these sensors in animals, whether we can actually monitor neurotransmission at the levels that we need to be able to do, and how that correlates to specific behaviors. Once we have that information, and particularly as we learn more about, for instance, what may be wrong with chemical neurotransmission in certain disorders, then we can begin to think about coupling these sensors. I would envision that this would occur, under pretty special cases. We're not going to be dropping things into the brains of everyone with a psychiatric or neurological disorder, but there are cases where we do have to invade the brain space in humans for treatment. Also, another example is, of course, for patients that have head trauma, right, where they already have to have some kind of a surgery. And they're already monitoring devices, early monitoring devices that we use in our own research that are currently approved for human use in those cases.
Do you have any timeline on that, when they might be used in humans?
So I kind of give a rough timeline, at least for our sensors in animals, that we're looking at about 5 years now. We just had our first demonstration. What I'll talk about today is a demonstration that these can actually work and do so over the concentration ranges that we expect neurotransmitters to be present at in the extracellular space. I think within 5 years we'll have devices that we'll be using in awake-behaving animals. And from there, it's probably another couple of years before we would be able to put those in humans. I know that DARPA already has a program, however, for looking at something called closed-loop monitoring. So these ideas are being pushed forward right now.
Okay, thank you.
Hi, Doug Dollamore, the American Chemical Society. I'm a little intrigued by using this technology perhaps to give us insights into some diseases or conditions that are eluding explanation quite a bit, like Alzheimer's or autism or Asperger's. Can you is that something that you're looking into?
Yes. Paul, do you want to speak a little bit?
Well, my lab is very interested in studying drug addiction. It's becoming an increasing problem in the United States. And we use an animal model for this to look at the impact of the exposure of drugs of abuse on the release of these neurotransmitters, dopamine and norepinephrine. But in the future, what we're really interested in looking at is identifying novel targets, new transmitters that could be altered in these disease models, and then develop some pharmacology to try to approach changing the activity of those new modulators. And the technology that we're presenting, these tools, will be able to give us clues on when and where these particular new signals are released. And that's our hope. We can also apply these tools to psychiatric models, but like Anne, we're really focusing on these animal models to be able to understand better the signaling pathways that change in these disease models, and then identify ways to adjust that so we could come up with new treatments and then eventually take this into clinical studies in humans.
Thank you. I'm Bob Service with Science Magazine, and I was curious because neuroscientists have, of course, known for many decades that about many of the different neurotransmitters and a lot of the dynamics that are involved there. And so, two questions: what do you get by studying them in real time? And then I seem to recall from when the Brain Initiative was announced, there was a lot of emphasis placed on beginning to try to understand networks and trying to say, can we use these kinds of tools to explore not just one neuron here or there, but how the conversation is happening, and can we study emergent properties and gain insights there?
Absolutely. I'd love to take that one. I think to answer your first question, I would disagree that we know a lot about neurotransmitters and what they're doing. I think one of the things that both Paul and I and others are trying to do in our work is to develop sensors that actually allow us to measure neurotransmission at the length, time, and chemical specificity scales that will allow us to extract information about chemical signaling. We are not there yet. We do have methods that can tell us some things about chemical neurotransmission, but we do not have sensors that can allow us to go in and measure at the scales over which information is encoded. And I loved your use of the word emergent, because I think that really captures a lot of what the Brain Initiative is about. And part of what emergent technologies will encompass is making high-density recordings. So one of the things we're very excited about in terms of trying to capitalize on field effect transistor technology is the ability to highly miniaturize these, which we actually already know how to do from nanotechnology and nanoscience, materials science, and to make devices that will have very high densities of very small recording sites. And so we can begin to capture, as you said, more network activity, what's happening with many neurons simultaneously, because we believe that therein lies the ability to begin to capture information encoding. Well, I think it's basically two things that will need to be pushed forward. The ability to highly multiplex our measurements, multiplex them in terms of single neurotransmitters, or as Paul said, also to be able to multiplex across many neurotransmitters, because we know that information is encoded not by single systems, which we've been highly limited to studying in the past. And then I think that collaboration, as we begin to gain information from these devices, in collaboration with computational scientists, to enable us to try to understand what this information will mean, will be highly important. Already one of my colleagues at UCLA, Sotiris Masmanides, is collecting action potential recordings, electrophysiological recordings at densities of 1,000 recording sites. And the information overload, even from that technology, is huge. So that's kind of what I envision. You're welcome.
Further questions?
Hi, Katie Cottingham from the ACS Office of Public Affairs. So I know the symposium deals with the BRAIN initiative. Do you have any information about upcoming rounds of funding or what's the status is overall for the BRAIN initiative at the moment?
Yes, we do have some information. I believe this year funding from NIH is expected to increase. I think it's going to triple in terms of their commitments to BRAIN Initiative funding. We haven't yet heard whether we'll have UO1 proposals solicited again this winter, but we're expecting that. NSF also has come out with their call, and they're going to be receiving proposals in October on neurotechnology, so we're really starting to see them get into the funding game as well. So,
Further questions?
Okay, so it's Kath from Sinai magazine again. Just to ask, I suppose, looking at the title of the press conference was "Watching Thoughts in the Brain," and I suppose most people will be more familiar with things like functional MRI for looking at thoughts in the brain. How does this sort of technology compare? Is this just another level of detail on that? And also, I mean, can you actually see differences already in the mice brains? Do different mice respond differently?
Yeah, I'll take that one. So we are, so the part of the brain that we've been looking at is the cortex, and a lot of the cortex is involved in making decisions and deciding to do something, take an action, take a drug, for example. And so the techniques that we have, we can now monitor these sort of decision-making cues, or thoughts, if you will, in real time. And then we can see the actions on the animal. For example, in our case, we're looking at licking to collect the reward, the sugar. The timing of that, so to be able to visualize this now, we can see, we're getting closer to the source. So the thing with fMRI is that you're looking at changes of blood flow and sort of inferring from this the activity of the brain. And here we're looking at the precise timing of a very specific chemical that's released, and then we can connect that with the actions of that animal.
Okay, thank you. Also, the release mentions, I think it's another type of sensor that you're developing for neuropeptides. Is that right? Can you say something about that?
Sure, I'd be happy to. And I forgot to mention, this is all in collaboration with my colleague David Kleinfeld at UCSD. And together what we're doing is we've already published the use of these tools in living animals, and we want to expand the technology to this large family of neuropeptides. The difference is the neuropeptides are made up of amino acids, and so they're like tiny pieces of protein, and they're found and distributed in many different types of neurons in the brain. But because they're released at such low levels, they're very difficult to measure with standard techniques. And so the tool that we're developing would allow us to now see the activity of these new neuropeptides and get a better sense of when are they released, where are they released, and hopefully why are they released.
So these new tools, they're not based on the CNF ERs that you sort of mentioned
They are.
earlier. Oh, they are.
They are.
They're similar.
And that's the beauty of our system, is that it's like a plug-and-play system. And the receptors that I mentioned in the very beginning, they're very specific receptors that interact with these chemicals. And so the first set of receptors we use, one was for dopamine. And that's how we created the sniffer that measures dopamine. Another sniffer, there's a receptor for something called somatostatin, which is a peptide. And now we can measure the activity of the peptide through this receptor.
Right.
So we're taking advantage of the body's own natural evolution of proteins that interact with these chemicals.
So how many of these neuropeptides or neuromodulators are there? I mean, how many could you extend this technology to?
Well, each of these, the family is, it's over 60, 70 neuropeptides. And each peptide interacts with a specific receptor. So in principle, we could make one for each one of these.
Also, you mentioned, I think, Anne, about the levels, and you implied that currently we're not able to measure the levels. Is that concentrations low enough?
Yeah,
So
I mean,
what can we measure at the moment, and what are you
Yes,
aiming for?
Absolutely. And we actually use the current technologies in our laboratory. So in some cases, we can get to concentration levels we need, but we sacrifice temporal resolution. Other times, we can get high temporal resolution for a few of the neurotransmitters, and then we sacrifice chemical selectivity, meaning we can't tell the difference, for example, with fast scan cyclic voltammetry very easily between dopamine and norepinephrine, which are chemically highly related to one another. And as Paul mentioned, when you start to think about the peptides, of which people have estimated there could be upwards of 100 of these different substances, then we're really outside of the realm of using kind of brute chemistry approaches. We need to start to capitalize on nature's ability to make receptors that are highly specific for each neurotransmitter. And so in Paul's work, as he said, he's capitalizing on the native receptors. In our work, we're actually kind of fooling nature into making receptors for us using nucleic acids, but we're still using the basic concepts that are used in nature's for receptive technology, if you would.
Thank you. So thank you, Dr. Andrews. Thank you, Dr. Slesinger. The archived version of the session will soon be posted at bit.ly/ACS Live Philadelphia. Please join us for our next press conference today at 10:45 on using fungi to recycle your used smartphone batteries. Thank you.